All right. So exam 2 is done. Most of you seem to have done really well. We are going to work on the grading early this week. Hopefully by Thursday, we will have your grades available. I don't anticipate any sort of panic or low grades. I think the grades are going to be pretty healthy. So we'll talk about that on Thursday of this week. So exam 1 done, exam 2 done. The only big assessment that's left is what? The final exam, which is going to be the last day of our class. Let's see, August 19th. So that's a Thursday. That's going to be our last class. 8 a.m. That's going to be our last exam. Let's see. And it's going to be a comprehensive exam, right? So there are going to be topics from start to the end. But that's a lot to ask in a final exam. So I'll give you guys some things to focus on so that you can prepare those areas really well. We will do that when we get as we get close to the final week. Okay, so what are we doing today? We are going to be talking about memory 5. This is our last lecture on a series of lectures on memory. Next class, we'll be talking about introduction to operating systems. So we'll not be designing operating systems, but we'll talk about some aspects of operating systems and how does an OS manage those functions. Today, we'll focus on memory. We're going to be talking about reliability and coherence, right? So some of the things that we talk about today, what I'm hoping is that you like the ideas and you actually maybe look at ways of using these ideas in other classes or projects that you may have. I'm specifically focusing on the reliability part of things. So when we have a memory, we just think that they don't forget, right? There's no data corruption. We talked about memory hierarchy, cache, DRAM, hard disk, but we never talked about what if there was error in whatever we write and read. So we are writing some data to a memory, no matter what level it is in, and then when we read it, maybe it got corrupted while it was there. How are we going to know? Well, a very simple idea that we look at in COCO, if you guys remember, we do this for like a slide, no more, was error correction using parity codes, right? So our exclusive OR, exclusive NOR gates were helping us generate those parity bits. And we looked at one example where we write something to memory and then we read it back, and then we check whether there was an error or not. So we did that very briefly in COCO. We will go into it a little bit deeper today. So we want our memories to not forget. We want fast, but if it is fast, but if it is not reliable, then it's of no use, right? So we want fast, we want cheap, we want big, but we also want dependable, reliable memories. So what we can do is we can build redundancy to make the memories such that they, even if there is error, we will be able to correct it. So, what we are going to be essentially talking about today is error correction, detection and correction. In general, detection is going to be slightly easier than correction, because it's one thing to say error occurred, it's one thing to say, oh yeah, error occurred over here, right? So depending on whether you are trying to do just error detection or you are trying to even do error correction, you may need more redundancy bits, right? So what is redundancy bits? They are not going to be increasing your data, right? That's not contributing to amount of data that you're storing. This is just on top of the data bits so that you, even if there is error, you know about it and you will be able to correct it. So regarding this idea, let me ask you a question here. What is the probability of 1-bit error? And what is the relationship of this guy with this? 1-bit error, 2-bit errors in the same number of data bits. What is the data bits and redundancy bits, right? All, whatever you're storing. Suppose you're storing 32 bits. If you're storing 32 bits and you read 32 bits back, what is the probability that 1-bit occurs, probability that 2-bit occurs in that 32, what is the probability that 3-bit occurs in that 32? I don't want their exact numbers, I just want the relationship. What do you think probability of, what is the highest here? I just want the inequalities. Good. 1-bit error is going to be the highest, right? And then probability of 3 bits in error are going to be the smallest. So if you have 1-bit error, the chances of that are going to be a lot more than probability of 3-bit errors. Now, if you go and look at some real numbers, you will find that probability of error, the bit error rates, can be very, very, very low, depending upon whether you're talking about memories or, say, applications like communications. Those numbers can be 10 to the negative 6 all the way down to 10 to the negative 18, right? So we are talking about one error in 10 to the 6 bits and as low as one error in 10 to the 18 bits. And if you now talk about 2 errors, then you can see that the probability bit error rate is going to scale that way. So you can say that as a general thing, probability of 1-bit error is going to be more than probability of 2-bit errors. I just want to point out that there is one scenario in which that is not true, which is called burst errors, right? So when you are going through, say, a wireless communication application, sometimes you can have burst errors, which means that a bunch of bits together are going to be an error. So that's not going to be relevant to this. So that's like a exception to this rule. This is in general. So probability of 1-bit error greater than 2 and greater than 3. So if I design some error correction and error detection codes that will allow me to detect and correct one error, that is much better than going for 2 and 3, right? So if I'm just doing it for 1, I'm doing a pretty decent job. I don't need to worry about the 2 and the 3. Okay. For this error correction and detection, I'm going to be using Hamming codes. Hamming codes are dependent on redundancy bits that are generated based on the parity of bits. Now you can have one parity bit and you can have multiple parity bits. So what you do is you have a bunch of data bits that you're trying to protect using these parity bits. You can generate some parity bits, redundant bits, and then you have data, you have redundancy bits, parity bits. Both together, you're going to call it a code word. And you're not going to store the data, you're actually going to store the code word and then retrieve the code word. So you'll store both data and parity, and you will retrieve both data and parity. And then you will check. And we will do that with an example here. So what is parity? Parity is simply the counting the number of words in a bit pattern, right? So if you have, say, let's take, right here, 1011. 1011 is a 4-bit word. And the number of ones over here are 3 ones. So you're going to call this odd parity, right? This 4-bit word has odd parity. So you're very simple, right? So you're just counting the number of ones. If it is even, you're going to call that even parity. If it's odd, you're going to call that odd parity. Pretty simple. Now, next, when a word is written into memory, the parity bit is also written. The redundancy bit, the parity is the redundancy bit, it is also written. In our case, we are just talking about 1 bit. We may have multiple. We may have more than one parity bit. So you're going to write a 1 for odd, and you're going to write a 0 for even. So what we'll do is, you see, 1011 was our data. This was our data bits, 4 of them. And I wanted to write this to memory with the parity. And I said this is odd parity. So odd parity, I'm going to write a 1 for it. So the parity bit that I generated was a 1, odd parity. So instead of writing a 4-bit word, I'll write a 5-bit word to memory. what will that be? It will be 1, 0, 1, 1, and I will pad it to the right with my parity bit 1. So what is the parity of this guy? Parity of the word that is written to memory will always be what? Even. Parity of written word, in this case a 5-bit word, will be even. Which means when you read it back, when you retrieve it, for any code word, you should be able to get an even parity, right? See, 0 for even, we don't change it. 1 for odd, so we change it from odd to even, right? So no matter what you store, whatever you retrieve should have even parity, and if it doesn't, we know that some error have occurred. What can you tell me about error? So let me ask you some true or false statement. If the parity of the retrieved word is even, you are guaranteed that no error has occurred. True or false? False, right? Why is that? Because there could be 2 errors or 4 errors. Even number of errors, you will change the parities back to even, right? So you could have even number of errors and get it that way. But what did we say? We said probability of 1-bit error is much greater than 2 bits and 3 bits. So probability for that 2nd bit error or the 4th bit error, that's going to be much smaller, right? So I'm sort of trying to ignore that. I'm just trying to be in the best of, just in the 1-bit error world. But that's absolutely right. It is not guaranteed. We may have had more than 1 error. Zach, you have a question? Now, we could also have 3-bit errors, right? If you have 1-bit error, yeah, your parity changes to odd. If you have 3-bit errors, your parity again changes to odd. But now, you don't know where that error has occurred, right? You know that error has occurred, but you don't know whether it is 1 error or 3 errors, and where are those 3 bits? So those are the problems associated with just using one redundant bit. You sort of know that there is error, but you don't know much about where that error is. Next, we'll build on it. You will see exactly how you can pick out the bit in error. The parity of the n+1 bit word, in our case, 5-bit word, should always be even. So whatever you write to memory, always even parity. So when you read it, should be even. If it is not, you know error has occurred. Questions here? Next, let's talk about parity code for error detection. We'll use it for correction as well. Now, in order to talk about the parity, the single error correction and detection, we need to define Hamming distance. What is Hamming distance? Well, it is simply the bits, the number of bits that are different in 2 code words. So I'm assuming that I have 2 code words. Both of them are 8-bit code words. Remember code word? Data along with parity is the code word. So I have 2 code words over here. I want to find out how many bits are different at per location, how many such locations are different. So I think we can clearly identify that's 1, that's 2, that's 3, everything else is the same, right? So Hamming distance over here is going to be 3. So this is defined as number of bits that there's water dripping from somewhere. All right, so you're doing location by location comparison. So Hamming distance over here is 3. Next. What do we want? We want Hamming distance to be 0, right? For the word that is written and then read back. We want that Hamming distance to be 0, which means that you want everything to be the same. Now, let's try to find, show the 9-bit pattern used to store 42. Okay, so we are going to try to store 42. We are going to generate that parity bit, and we are going to pad that parity bit all the way to the right. Now, there is no such constraint, right? So there's no such rule that you have to put the parity all the way to the right. You could actually have some parity bits go in the middle of the code word as well. Actually, their location matters to the algorithm. So for this particular simple case, we are just assuming that we are putting it. Okay, am I sweating or the thing is leaking? I'm not sweating. All right. So 9-bit pattern used to store 42. What is 42? 42 is shown right here, right? You can do that decimal to binary conversion pretty easily. What is the parity bit going to be for this? So these are data. That's my data. 8-bit data. What's my parity bit going to be? 1. So I've got 1, 0, 3 ones in there. So odd parity, so my parity bit has to be a 1, right? And I'm going to place that all the way to the right based on my assumption over here. Parity bit is located all the way to the right. So my code word that I'm going to generate for 42 is this code word. And in this case, 9-bit, because 8 bits from data, 1 bit from parity. You have got 42, 0, 0, 1, 0, 1, 0, 1, 0, and then all the way to the end, I will pad my parity bit 1 there. Just an example. Now, suppose you take this, right? You store it. Now you're trying to read from it. When you read it, you get this. Let's just assume that we get this. Should the system signal an error in this case? Should, yes, right? It should, but will it? If you just look at the parity, it has to have even parity, right? 1, 2, 3, 4, 5. 5 ones. So the parity of this code word that you retrieved is odd. So yes, you should have signaled an error. And in this case, it will signal an error because read word, 9-bit word, has odd parity. We know that we write even, we should read even parity. All right, next. Now you have read this. You saved 42. You read this from memory. Should the system signal an error? And will it? It should signal an error, yes, because this is different from this, but it will not signal an error because the red word is even, right? No, it will not, but it should have. We had some errors, right? It's different from 42 that we stored, but it's not going to signal an error because the parity of the code word that you read is even. So that's a possibility. And we talked about this, where you could have even number of bit errors, and you can still maintain that even parity, so that gets missed. You don't check, you don't signal error in that case. All of this to say, we would need more parity bits if we want our algorithm to work really well, right? We would need more bits, more redundancy bits. Now, what you don't want is the number of data bits to be comparable to the number of redundancy bits. You don't want that. So you don't want that to be that high, like 8 bits. You cannot protect 8 bits with 8 redundancy bits. That's going to be, well, useless. You don't need it, actually. If you wanted to do just error detection and correction for 1-bit errors, then you can get away with 8 3-bits. You will be able to do it. So we'll take an example, look at an example of how we can do that. Questions so far? Pretty straightforward? All right. I'm hoping that soon it'll get interesting for you. What about correction, right? So that was detection. How about correction? We are going to know whether did error occurred or not, But the more difficult problem is, where is this error? So for that, we are going to go into an example. We'll take a look at Hamming Error Correction Code, ECSE. So far, we were just detecting. Now we are going to detect and correct. In this, all the code words are having a Hamming distance of 3, which means you take data, you generate their parities, you have a code word. If you look at all the different code words, they are going to have a minimum Hamming distance of 3 from each other. So this is minimum number of bits that are different between any two code words. So the code words will be generated in such a way, which has both data and parity, that they will always have a minimum distance of 3 between them, any two code words if you pick. Now, one of the getting a minimum distance of 1 is pretty easy to see, right? Because you have one data sequence, the other data sequence is going to be one different at least. You guys see that? That is going to have one different, like for sure. But because you are now going to pad it with parity bits, multiple parity bits, those parity bits are going to also be different for the code words, which will make the minimum Hamming distance between any two code words to be more than, at least be 3. Now, if we use a code that has a minimum distance of 3, then any single bit error would be closer to the correct pattern than any other valid pattern. So let's suppose you have a code word, right? Over here, you have a code word. Let me just draw a circle here, and I'll draw a circle here, and I'll draw a circle there. And in this, I will say a code word. That's the actual thing that you are storing to the memory. And then you have over here code word with one error. Right? So you got one error. What is the Hamming distance between code word and the code word with one error? What is the distance here? 1. Number of bits that are going to be different is going to be 1. Now, on the other side, I have all other code words. All other code words, meaning all the other possibilities of data and parity, which we have already said they are going to have what? Hamming distance of 3, minimum. Minimum Hamming distance equals 3, right? So if there is an error, it is going to be closer, whatever that error code word is, this is going to be closer to the actual code word than all the other code words. You guys see that? So that's just being captured in this. So if you have an error, so if we had 2, then we would have been in trouble, right? Then it's equal. If you have 3, then you're saying, okay, my error, even if you have error, you're going to be closer to the actual code word than all the other code words because they are at a distance of at least 3. You guys see the logic there? And how are we going to generate that Hamming distance of 3? We are going to need more parity bits to be able to at least generate that minimum Hamming distance of 3. 1 is pretty easy to get because those are the data bits will give you that 1. So we need at least 2, right? So we need 2. You guys remember this word, number 2. We need 2 other bits to be different. All right, next, extra parity bits are going to allow the position identification of a single error. So more redundancy bits, that extra parity bits are going to allow us to find the location of where that single error has occurred. This only works for single error correction. Now, code word length. Well, you have some data bits, you have some redundancy bits. Let's assume that you have redundancy bits of R. You have R redundancy bits that what you generate is a code word of length 2R, 2 to the R minus 1, which essentially means using this Hamming error correction algorithm, you would need R bits to protect 2 to the R minus 1 as a code, right? And so you see, code word is this, redundant bit is R. What about data bits? How many data bits are here? 2 to the R minus 1 minus R, right? R is the number of parity bits. So what I can say is, let's assume example, R is 4. So if you have parity bits, four of them, then how many data bits can you have at max? Data bits and code word length. So 4 to the, this is going to be 15, right? That's the maximum you can go. You can always have 14 or 13, but you're just wasting it in that case. All right, then 11 data bits, right? So if you had data bits that were more than 8, like here in this case 11, you're going to need 4 redundant bits to protect 11 data bits. Total, there are 15 code word, bits in the code word. This is going to be for single error correction. Questions here? What is R? What is the length? What does it mean by code word length? What is data bits? And of course, R is going to be an integer greater than 1, so that's pretty easy to see. Okay. Now I'll lay out the algorithm for Hamming error correction codes. So what I'll do is I'll start numbering the bits from 1 on the left. So I have the top row over here indicating bit position. We are generally used to starting it from 0, but because I'm talking about the location of the bits, just to be simple, I'll start with 1, right? So I have bit position 1 all the way down to bit position 15. So I have 15 bits for what? For my code word. What does my code word have? Data, parity. Where is the data? Where is the parity? I know that I need 4 parity bits. R was 4 in our example. So where are the 4 parity bits and where are the 11 data bits? Those are their locations. So parity bit number 1 goes in bit position 1. Parity bit 2 goes in bit position 2. Parity bit 4 goes in position 4. Parity bit 8 goes in position 8. So there are 4 parity bits called P1, P2, P4, and P8 going in positions 1, 2, 4, and 8. All the other locations are for data bits. D1, D2, D3, D4, D5 all the way to D11. So you've got 11 data bits, 4 parity bits, and the locations are such that you are following a power of 2, right? P1, P2, P4, P8. There's a reason for that. And I'll talk about that reason on the next slide. So those are the bit positions. These are the encoded bits. Some are parity, some are data. Both combined make your code word. What do they cover? Parity bit coverage. Each parity bit covers not just one, but it actually covers more than one bit. Let's try to see. P1, well, P1 is right here. Okay. P2 is right here. D1. D1 is what? At location 3. How do you get to 3? 1 plus 2. You got P1 covering it, P2 covering it. So D1, a data bit, is covered by 2 parity bits. How about D2? 1 plus 4. It is covered by P1 and it is covered by P4. 2 parity bits. Look at D9, which is at location 13. It is covered by P1, P4, P8. Now, if you look at all the data bits, you can come to a conclusion that each data bit is protected by at least 2 parity bits. Right? Now you go back to our discussion about the minimum distance of being 3. You got 1 definitely because of changing data bits, and you got 2 because of these 2 parity bits protecting each data bit. That makes it at least minimum 3 away for all the code words. All right, let's come back here. So so marking the positions, right? That's marking the positions pretty easy. So now what we are going to do, well, I'll give you some data bits. You generate the parity bits for me. Then you tell me what you're storing. And then we'll do the exercise in reverse. I'll tell you what was stored. You tell me whether error occurred or not. If error occurred, then you tell me where that error was. Right? We'll do the entire process. Let's see, what else do we mark all the bit positions, power of 2, we talked about that. All of the bit positions are used for data. All right, straightforward, we talked about that. So we know where the parity bits go, and we know exactly where the data bits go. What I do is I'll just mark out the parity bits first, and then all the other blanks will be filled with data bits. That's what I find convenient to do. Let's see. And you look at P1, it's like the least significant bit on our truth table, right? Alternates. And P2, and that's like next to least significant. 2, 3, 6, 7, 10, 11, so on. What about P4? Next significant. 4, 5, 6, 7, and all of those. And then 8, all of the 8 here, right? So this is almost like filling out a truth table, right? Which is why those bits are taken, because they protect each location in the code word. Let's see. So the position of the parity bits determines the sequence of data bits that it can check for. So for example, bit 1 or parity bit 1 was checking for the alternating bits, right? In 1, 3, 5, 7, 9, and so on. What is unique about 1, 3, 5, 7, and so on? What is common to all of that? The least significant bit in all those numbers is a 1, right? And if you look at bit position 2, bit 2, your parity bit 2, it was checking for errors in that, right? So it is checking for 2, 3, 6, 7, and so on. The bit that is a bit more significant than the least significant bit is always 1 for all those numbers. And similarly for bit 4 and bit 8 and so on. Let me just, for the sake of completeness, go for a slightly different question here. If your redundant bits from R is 4 here, what if you had to go for 5? Could you make a similar table if it went to 5 redundant bits? What would be the length of your code word? 2 to the R minus 1, so it will be 31, right? So 31 code. And then how many data bits can you protect with that for single error correction? 31 minus 5, whatever that number is, 26, right? Let's see. So you can have, how would this change though? You will have P1 here, you will have P2 here, you will have P4 here, you will have P8 here, you will have P16, right? You will have P16 at bit position 16, and then you can fill in all the other data bits, 1 through 26. Can you see that? So I hope you will be able to scale with this as well. And even when you do that, you will see that the parity bits, you will have at least 2 covering each data bit. All right, let's move on. We talked about that. Note that each parity bit is covered by 2 or more parity bits. Yes, we talked about that. Set the parity bits to create even parity for each group. So this is important. Let me just mark this. The way we are going to generate these parity bits is going to be such that each group has even parity. Now you have groups, right? So you see the group number 1 has what? P1, D1, D2, D4, D5, D7, D8, D11, all of that belong to group 1. And then all the X's over here, those are group 2, then group 3, then group 4. So what you're doing is you already know the data bits. You're generating these parity bits such that each group will have even parity. Let's see that. Let's do an example and then we'll know. How do we know if there is an error? Well, you have made sure that each parity bit, P1, P2, P4, P8, were determined such that each group was even parity. So when you read it back and check for the parity, all of them should be 0, right? If there is no error, you should get even parity for all those. So if you get something like this, when you read this back and do your calculations, if you get P8, P4, P2, and P1 to be all zeros, then you know that there is no error. Because the way you generated them was by looking at the groups, and you make sure that your P's were all even. You guys see that? The way you generated the parity was such that each group was even parity. So when you read it back from memory and then recalculate your parity, you should get even back, right? So you should get even for P8, even for P4, P2, and P1. If that is the case, you know there's no error. However, if you read it back and recalculate your parity bits, if you get something like that, P8 is 1, P2 is 1, then you just do 8 plus 2, 10. Bit position 10 is going to be in error. So you just flip it. You see how elegant that solution is? And we'll see it work. Correct the error by inverting that value in bit position 10. Because bit position 10, look at this. Bit position 10 is covered by P2 and P8. So if those are in error, you just flip that bit position 10, which is in this case data bit number 6. All right, let's do an example, and then hopefully we will be able to relate more to this algorithm, right? Now, this is before you store, right? Before you store, you have to generate all your parity bits. So assuming that we are dealing with 1 byte data, so we have got 8 bits over here, and to protect these 8 bits, we are going to need 4 redundant bits. We will deal with a 12-bit Hamming code. So our code word length is 12. I've got 8 data bits in there. I've got 4 redundant parity bits in there. I'm going to need to generate them. So what I'll do is I will put out some blanks here to indicate where the parity bits are going to go. That's P1, that's P2. That will be, okay, well, let me just draw the blanks here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. Now the question is, where is what going to go? Well, P1 was supposed to go here, P2 was supposed to go here, P4 was supposed to go here, 5, 6, 7, 8. P8 was supposed to go here, right? I don't know these guys yet. But all the other data bits, I know. Right? Let me just fill those out. 1, 0, 0, 1. So I've got 1, 0, 0, 1, and then 1, 0, 1, 0. 1, 0, 1, 0. Right? I see that? So that's my code word. I don't know where I don't know the parity bits yet. I have to generate them such that each group will have even parity. But I know the data bits. I have put them in their respective positions. Now, what is P1 going to be? Well, P1 is covering what? Bit position 1, 3, 5, 7, and so on. So I need to generate P1 in such a way that the highlighted positions should have even parity. So what should be P1? So I've got 1, 0, so number of ones, right? 1, 2, 3, 4. The parity of this group is already even. So what is P1? 0. Next. Let's do it for P2. So P2, what is the coverage? Blank, 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 blank. So number of ones, I've got 1, 2, 3. So what should be P2? 1. All right, looks like this is too simple for you guys. Let's see, P4. What is P4 covering? That, and then I have 1 blank, 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 and then that, right? So these 4, and then these 4 are blanks, and then you have that. So what is this? P4 should be what? There's only one, so 1, right? Next, I'm going to erase this, and I'm going to try to generate P8. What is P8 going to be? P8 is checking for 8, this, and this, right? And so on. I don't have those yet because there are going to be 8 of them there. So what is P8 should be? P8 should be 0. Yeah. Each group now has even parity. You guys see that? So what am I storing here? I am storing 0, 1, 1, and 0. That's my 12-bit Hamming code for the 1 byte data that was given to me, right? So I will not store this. I'll store this to my memory. Now, there's a point of confusion here. You see over here, it says P4, P8, and P2, P1. If there are only zeros, error has occurred. Well, there are not zeros over here. So did error occur? Well, so that's the thing, right? You are going to have to write it, read the code word back, regenerate your parity bits, recalculate the parity bits, right? You have, when you recalculate them, that's when you are checking whether they're all zeros or not, right? You're not doing them here. We have not even written this to the memory yet, right? So I hope that you avoid that confusion. All right, so we have come up with the Hamming code. Let's see how we can put it. So this is the same one as before, hopefully. 0 1 1 1 0 0 1 0 1 0 1 0 0 1 1 1 0 0 1 0 1 0 1 0. Okay, so that's the same one as before. You have written to memory, right? Now what we read from memory was this. Just an example, right? Suppose you are writing this guy, but you are reading. When you read from memory, let us say that it was this guy, right? So clearly there is 1 bit in error that is highlighted in red, but algorithmically, how are you going to find that out? We are going to find that out by looking at the parity of each group, right? So what is group 1? So let's see, group 1. Group 1 is all the alternating ones, right? So let me just write down the code word first. I've got 0, 1, 1, 1. Then I've got 2 zeros, then 1 0, then 1 0, then 1 0, right? So I'm going to highlight group 1 first, which is in blue, say, alternating. What is the parity of those? Parity here is P1, which is what? 1, 2, 3, 4. Even parity, 0. Yeah? Okay? P1 is good. So right away, I know that there was no error over here. There was no error that P1 was covering. All right, let's move on. Group 2. For group 2, I have the same code word. Oh, actually, I'm going to say something else. This one will tell me this is okay, right? Then for this guy, I would need to do this. Regenerate my parity bit. So highlighting what? 2, 3, blank, blank, 2, blank, blank. All right, so what is the parity here? P2, what is it? 1, 2, 3, 4. Should be 0. 1, 2, I think I messed it up somewhere. I copied down the right one. Yeah, I need the error one. Yes. Okay, so 1, 2, 3, 4. All right. So the first one is fine. The second one should be, the reason is I know the answer, and this was not going to be, that's how I got that. So P2 should be 1 here, right? So I need to copy this. I copied the one without the error. So of course I will have even parities. There's no error. All right, so we got P2 is in error. All right, let's do that for group 3 now. Uh, Same strategy. Let's just do some erasing quickly. Change that, change that, change that. Now highlight. P1, P2, data P4, 4 of them. Blank, 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 and there. All right, so what is this? 1, 2, 2 of them, right? So if this is 2, this is P4, this is going to be 0, so this is going to be okay. So it has even parity here. Next, last one, group 4. It is, I'm just checking the parity of each group. 8, right? So if I want 8, I can actually, yeah, all right. 1, 2, 3, 4, 5, 6, 7, 8. All right. So I've got what? The parity 8th bit, number of ones, 1, 2, 3. So I need a 1 to make it even. So let's see, this is going to be an error as well. You see that? So 1, 0, 1, 0, that was your parity bits, indicating that there was an error where there was a coverage for P8 as well as coverage for P2. Which bit had coverage of P8 and P2? P2, this guy here and this guy here, right? So whatever you have in bit position 10 was in error. So you just flip it. That's how you know that this guy will be in error. You will flip it. And it's 10, right? 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you flip it. Go ahead. Parity bits, you have to, you are assuming that the parity bits are not in error. So yes, some limitations on the algorithm. More limitations will follow. So yes, yeah, that's a problem with this one. All right, let's go on and take a look at that second idea. This is just an idea again. Single error correction, double error detection. So can I have more parity bits, because I'm going to need more than R of them, to be able to do a single error correction, but let us see if we can do double error detection. Oh, no, hold on, hold on. No, this one will be okay. Even for parity bit, this one will be okay. You will get something like this for the 4 parity bits. This one will be okay. If you get something like this, when you read it back, that means the parity bit 1 was in error, right? Because 1 is only covering this, P2 is only covering this, P4 is only covering this, P8 is only covering this. There's only 1 bit there. So that's the only one that can be in error. You see that? Yeah, so there is a, yeah, this one doesn't have a problem. Parity, even if parity bits are in error, you will be fine. Yeah. For the next one, you have this. This guy has that problem, where if parity bits are in error, then it causes trouble. So single error correction, double error detection. We are going to need an additional parity bit for the entire code word. Let us call that PN. So now we have parity bits, and now we have the parity bits for each group, and we have parity for the entire code word. So we have PN for the entire word, and then you have all those P1, P2, P3 for each group. Because we have one more thing that could change, you have the Hamming distance of 4 now. Let H represent the single error correction parity bits. So H is simply a set of bits P8, P4, P2, P1, like our previous example. So you've got these parity bits for each group, and then you have got an additional parity for the entire code word. 4 things can happen. You can have H to be even, which means that the parity of the parity bits is even, right? This is the parity of the parity bits. Parity of the parity bits could be even or odd, while the parity of the whole word could be even or odd. So 4 possibilities happen there, right? H is even, Pn is even, H is odd, Pn is odd, even, odd, odd, even. So if both are even, that means that no error has occurred. If both are odd, that means that you have a correctable single bit error. So you can do SEC. If you have H as even, Pn is odd, there is error in the Pn bit, the parity in the nth bit. And then if this is odd, this is even, you know that 2 errors have occurred. So it's slightly more powerful than single error correction. But if 2 errors have occurred, we don't know their position yet. This is what is used in error correcting dynamic RAMs. They protect 64 bits with 8 bits. So we are just going to lay out its features here. We are not going to do an example. But the idea is have more parity bits, have one more parity bit. You have parity of the parity bits, and you have parity for the whole word. You have essentially 2 parities giving you 4 possibilities. Depending on which possibility, and you can match it. So it involves analytical proof that supports this. Both are even, no error. You can have a single error that could be corrected, so that's SEC, or you can have that nth parity bit being in error, right? Single error correction protects all these guys and all the data bits. It doesn't protect PN. Error in the PNth bit is indicated by this even, that odd. This is odd, this is even, you know 2 errors have occurred. We don't know their location. Good. Like, absolutely, yeah. So the more complex your error correction algorithm is, the more expensive your RAM is going to be. Let's move on to our second topic for today, which is cache coherence. And the idea is this. Every processor gets its own private cache, right? So what I'm going to do is show you 2 views, one here, which is logical view, which is missing some realistic aspects. And then I'll talk about the realistic aspect of cache. If you have a memory system over here, which is accessed by, which is being considered as a resource for 4 different processors, P1, P2, P3, P4, we just think that, all right, P1 wants some data from the memory, it's going to get it. P2 wants some data, it's going to get it. P3 similarly, P4 similarly, right? So as a logical view, we don't pay attention to some memory inconsistencies that could happen. because of the presence of cache for each processor. Where is the cache? Very close to the processor, right? So each processor gets its own private cache, indicated by this $sign. Expensive, close to the processor, right? So you have got cache for P1, cache for P2, cache for P3, cache for P4, right? Now what could happen? Well, P1 could say, I want something from memory. Okay, the moment P1 says, I want something from memory, a block of words, those block of words, if they are not there in its private cache, they will be brought from memory into its private cache, right? And then now let's say P2 does the same thing. P2 says, hey, I need that same thing from memory. So block of words from memory brought into private cache of P2. Now P1 says, all right, I read this, I want to change it. Now if P1 changes, it'll look at it in the cache first, right? And if that word, block of words is in the cache, it will just write to the cache. Did the private copy of the same thing change over here in P2? P2's private copy did not change. P1 made sure that its own private cache gets updated. And if it is a write-through cache, you know that later on it will write through to the lower levels of the memory. So it will write through the memory and the hard disk, it'll do that. But what about the private cache of P2? Private cache of P2 is now going to have inconsistent data, right? You guys see the problem there? So we are going to need some mechanism where P1 yells out to the world or all the other processors that, hey, I changed, I messed around with this memory allocation. Whatever you have is invalid, right? So just discard whatever you have for this particular block of words. You guys see the problem with the cache coherence? It arises when there are multiple physical copies of one logical memory location. For example, multiple copies of each clash block. Copies will become inconsistent when write happens, right? If you are just reading, then there's no problem. Nobody is making any changes. If one processor makes a change, then that's what is going to create that problem. Now, let's see, does it happen in a uniprocessor system? Does this sort of problem have even if they are multi-level cache, level 1, level 2 caches, even then it doesn't happen. Because when you do, so you're assuming that when you are changing things in cache, you're doing write through, right? So you will write to all the lower levels of the memory. So if you write it to L1, you will write it to L2, DRAM, SDD, hard disk, you will do it for all of them. So if you just have one processor, then that's not the problem, because that hierarchy for each processor is maintained consistently. If you have another processor here which has its own private cache, then that's what gives this problem. Then we have that problem. All right. We'll do an example here. Hopefully this will be clear, and then we'll talk about some solutions here which are hardware based. So suppose you have a single memory location X. We are going to read and write to that location X by two processors, A and B. We are going to initially assume that neither cache contains the variable X, and it actually has a value of 0. So X is pointing to a location, an address in memory. It has a value of 0, initialized 0. A and B are two processors. Both of them have their own private cache. Neither of them have a memory location X in their private cache. After the value X has been written by A's cache, let me talk about this as I go through this table. So for each time step, we are talking about the event that happened, cache contents for CPU A, cache contents for CPU B. These are private caches for A and B. And then in the lower level, the physical memory contents for location X. So that's the lower level, which is common to both the processors. So in time step 0, we don't do anything. We just initialize it in the memory. A doesn't have a copy, B doesn't have a copy, we are not reading or writing, we are doing nothing in time step 1. We just assumed in time step 0 that memory contents for location X are 0. In time step 1, say our processor A reads that memory location. So as soon as it reads, whatever is there in the physical memory is going to be brought to private copy of cache A. Private copy of cache B, nothing over there, no change. And then X was not written, so that doesn't change either. In time step 2, CPU reads, CPU B reads. When CPU B reads, you have this old copy there, new copy from memory to CPU B, and then we didn't change anything, so memory is going to be X as well. For X, location X, memory, that value is 0. So here we have a consistent. This is consistent so far. Right here is consistent until time step 2, we are good. We have everybody saying at X, we have 0. Everybody is saying that. So we have a consistent memory there. Next, in time step 3, CPU A stores a 1, writes a 1 to X. When it does that, it changes its own private cache to 1. Private cache of B doesn't change because A is not responsible for that. But if it is a write-through cache, then A has updated all the lower levels. So it has also updated the memory for that same cache line. Right? So now we have a problem here. One of the problems is if you asked B for the value at memory location X, it's going to say 0. The other problem is if processor B were to write to memory for the same location X, it would write 0. It would overwrite the 1 that X processor A changed it to, right? So that's a problem, right? So processors are not able to agree on the value at memory location X. That's an inconsistent memory. We don't want to have that. We want to have all the caches in coherence, because as you are making progress on each process, you cannot assume, different processors cannot assume different values at the same location. So the problem was that A's cache and memory both contain the new value, then B's cache does not. If B reads the value X, right? Let's see, if B at time step 3, B says, I want to read X, it'll read what? 0, right? There will be a cache hit because it is there in the cache, then you will get a 0 for it, right? You guys see what I'm explaining here? At time step 4, and at time step 4, let's say CPU B reads X. If CPU B reads X, CPU A content is 1, CPU B, well, for CPU B, it will be a cache hit, right? Because it will find it in its cache. It will be a cache hit. So it will not go looking for it in the memory. If it did that, it would have been actually good because it would have found the right value. But it will not. It found it in its own private cache. So it will say 0 here. But that's inconsistent. It got it wrong. You guys see that? So yeah, a solution could have been if there was some mechanism to say this particular cache line is now invalid, all the corresponding requests for that particular cache line should result in a miss, cache miss. So you have got to go to the memory. Go ahead. Yes. Yeah. So it will never need to go to the memory. So it'll say, yeah, I'm good. I'm just finding it in my cache. So it'll keep doing it fast. Little does it know that actually the value is different. Questions? Oh, why do we have two CPUs use the same memory? Well, how many memories are you going to have? How many physical RAMs will you have? How many hard disks will you have? If you have multiple, it's not just cache that is different, but even if you have different RAMs and different hard disks for each processor, then what is the whole point? You have more processors so that you can make progress on a particular process. Where is the process? In the memory. Now you are going to need one thing that sort of maps out at least one layer in memory that has to be common, right? The whole point of having multiple processors is so that you can make progress faster on a process. Processes are instructions in memory. So they have to have be in the same memory. If they are not, then how are they going to communicate? But for cache, the application is different, right? Something very, very close to the processor so that whatever, and this is based on locality, I'm trying to access these particular memory locations. If I find them very, very close to me, then it's going to be very good. I'm not going to need to go to my big memory, right? Which sort of gives us that illusion. All right, so I hope that I answered that question. Let me go here. Coherence. The memory system is, when is it considered to be coherent? A memory system is coherent if any read of a data item returns the most recently written value, right? Most recently written value of that data item. Whatever you updated to for that particular memory location, that's what you have to read. It's very simple, this definition, but the reality is a little bit more complex, and we'll talk about what are the different things that need to happen in order for memory to be cache to be coherent. Three things have to happen essentially. We need to preserve the program order, the view of the memory has to be coherent, and there should be write serialization that is maintained. And each of these conditions, we'll take a deeper look into it by looking at them as a block diagram. So what is preserving the program order? Instructions have to be in order, right? So write followed by read by the same processor with no writes in between returns the value written. So let's suppose that you have a processor P1 here. You have certain address that you are reading and writing, reading from, writing to, and there's another processor P2 over here. In this particular condition, which is preserve program order, P2 is not playing a role. Only P1 and the memory is playing a role. So if you are trying to write followed by read with no writes in between, right? So you're saying write and then read, write and then read. Then you have to have the same value that you just wrote, right? So for example, if A wrote 1 to X, if it reads, it'll have to get 1, right? It cannot get 0. You guys see that? So it's just preserving that write, read, write, read, write, read. So if it keeps adding by 1 and stores it to memory, then whenever you read, you need to read 1, 2, 3, 4, and so on, keep incrementing. So in the previous example, if CPU A were to read X after time step 3, it should see the value 1, that because it just wrote that. So it's preserving that program order. Next, coherent memory of the view. So let us suppose that P1 writes to the memory address and P2 reads from that same memory location. Then if this condition says whatever P1 writes, P should read that same value for that same memory location if they are sufficiently separated out in time. You cannot obviously do that very, very close in time because of setup and hold time requirements. You're writing to memory, you're reading from memory. So you know that there are going to be certain limitations on setup and hold times. Data has to be stable in the memory before you can read it. That's setup time, right? Let's see, P1 writes X. P2 should read X for the same value. P2 will see the value written by P1 if read and write are sufficiently separated out in time. So let's say that location X, P1 says, I'm writing at X, I'm writing 10, right, to this memory location X. And after sufficient time has passed, P2 reads X. So when it reads X, it should say add X, it should get 10. If it gets 20, a different value, then we are not consistent in terms of our memory view. We are not coherent in our memory view. So in our previous example, we don't have this mechanism yet, but we need a mechanism so that the value 0 in the cache copy of B is replaced by the value of 1 after the CPU A stores 1 into that memory location. Right? So if I go here, you see in time step 3, CPU A says X is 1, CPU B says X is 0. We needed some mechanism to make sure that CPU B also agrees and says X is 1. We don't have that mechanism yet. One way could be because processor A changed the location, it is responsible to let all the other processors know that, hey, I changed this particular cache block or memory location. And then everybody else says, all right, we are going to drop that particular value. We are going to make it invalid. And if we need it again, we'll get it from the memory. Right? So the private cache that actually changed it, wrote it, is responsible to make that information available to all the other processors. That's one solution. We'll talk about the other. Next is write serialization. The third criteria for memory coherence is write serialization. All three conditions should be met. Only then you can say that memory is coherent. Writes to the same location by different processors are seen in the same order by all the other processors. So suppose that you have 3 or 4 processors, right? A, B, C, D are the processors, and they are writing to the same memory location. And we have a situation where A is writing first, B next, C next, and D last, right? So all the processors have to agree that that was the order in which they were writing to that memory location. There cannot be mismatch here. All the processors have to be in agreement that A wrote first, B second, C third, D last. That's write serialization. So if multiple processors are writing, everybody should agree that P1 wrote first, P2 wrote next, and so on. The order in which the writes happened should be agreed upon by all the processors. So if CPU B say stores 2 in memory address X, right? It was 1 when A changed it. Now if CPU B says store 2 over there, the processors should never be able to read the value before, right? The one earlier. The processor should also always say, yeah, B wrote 2, so we are going to treat that as our most recent value. We are not going to be able to read 1, which was done by A in an earlier time step. And they should be able to agree that A wrote first, it was 2. They should know when that happened, and then B wrote 2, that was happened later, and they should know that. Questions about the three criteria here? One is about preserving the program order. So that's just one processor with itself, right? Write, read, write, read, write, read, write, read. I should be able to keep on getting the most recently written value. Next is all the processors, this is the most important one, right? All the processors saying that at each location it is the same data. Second one is the most difficult to obtain. The third one is, if you are able to achieve the second one, the third one becomes easier. All the writes to the same memory location will be agreed upon by all the processors. Now, to do this, we have some software-based solutions. We have some flush or invalidate CPU instructions, hardware solutions that are far more common. We are going to take a look at a couple of them. There are some hybrid solutions as well, both hardware and software combined. So for example, like flush instruction writes all or specified cache lines to memory. So it takes in whatever you have written for the CPU, it writes all the other caches, private caches as well. Invalidate by the owner of the cache line, whichever cache changed it, wrote to a particular memory location on maybe a common bus, sends out an invalidate signal so that all the other caches have to drop that same cache line. Let's take a look at that snooping protocol, which is a hardware-based solution. So every cache over here that has a copy of the data from a physical block of memory also has a copy of the sharing status of the block. So two things have to come with the data. One, the data. Second, the sharing status of the block, right? Block of words in physical memory. We have had this discussion before where, when you're trying to read a particular word from memory, you don't bring just that word up, you bring the entire block up to your upper level to leverage locality. Next, the caches are all accessible via some broadcast medium, say a bus or a network. That sharing status, everybody should know that. And there are cache controllers that are going to monitor or snoop on that particular broadcast medium to determine whether or not they have a copy of the block that is requested on the bus. So let's take a look at this snooping protocol in action with an example here, and hopefully we can see how we can maintain cache coherence with a snooping protocol. So cache is going to get exclusive access to a block when it is written. Of course, if a particular processor wants to write to a particular block of memory, you can have multiple blocks writing to it at the same time. Yeah, you can do it separate in time, but you cannot do it exactly at the same time. Now, if you want to do it at one time, you need to have that exclusive access. So if processor A wants to write to a particular block, it's going to first get exclusive access, then it's going to write. And then the later problem occurs, right? How are you going to update the private caches of each of the other processors? Once it writes, once a private cache copy is changed, it will broadcast an invalid message on the bus. Everybody, all the other processors, I have changed the value at this particular memory location. So invalidate that particular memory location if it is there in your private caches. That's what A has to say, right? The owner has to say, whoever wrote to that memory location. So subsequent read by any other cache misses, right? So whenever the next cache, the moment you have an invalidate message on the bus for a particular memory location, for a particular block of words, after that, if any processor is going to try to, not the owner, all the other processors, if they try to access that same thing, if they try to read it, it is going to read it or write it, it is going to result in a cache miss. If it results in a cache miss, they are going to have to go to the memory to get it. And in the memory, they will find the most recent value because of a write-through cache. Owner is going to supply that new value in the memory as well. So let's take a look at an example, similar one to the one we did before, but we also have an additional column here that monitors bus activity. So CPU activity over here, bus or the snooping medium over here. Then you have CPU A's cache, B's cache, and then in the memory, in the next level in the memory. So there's no time step here. Initially, what we are doing is we are assuming that at X we have 0. The value is 0. And the first thing that A is doing is A is trying to read X. So if A is trying to read X and it is not there over here and over here, well, it's not there over here, it is going to result in a cache miss. So that is the message on the bus, cache miss for X. So what is that going to do? Well, you're going to have to look at the lower level, bring that particular block of words into the private cache of A. So that changes to 0 over there. This, no activity, and this remains as is. Nothing has been written. In the next time step, CPU B reads X. Well, CPU B doesn't have X over here. So that also results in a cache miss for X. So you bring it from the lower level to B over here. Next, CPU A writes a 1 to X. When it does that, it changes its private cache, but also sends out an invalidate message for that memory location X, so that B knows that it has to drop its value in the cache for that location X. No cached copy. Memory location in the lower level is still the same, 0. It has not updated yet. CPU, when it tries to read it, right, in the subsequent time step, you have CPU B trying to read it. Now, because it dropped its private value, right, from its private cache, it has erased that copy. It's going to result in a cache miss. If it results in a cache miss, it is going to say, all right, who changed X? Owner has to supply the owner, right? Whoever changed that private, the value of X has to supply the most recent value. So A gives it to B, also writes it to the memory. Now, this is sort of an example of a write-back cache, where the cache changes, but it doesn't write to the lower levels immediately. The writes to the lower levels happen when there is a read operation for it, right? Only when it is required, we will update the lower levels. That's what is happening over here. Questions about this example? So we have a consistent memory here, right? Because the owner is taking care of letting everybody know, drop this particular cache line so that they have cache miss, and then they go looking for it if they need it. Next, the problem with the snooping protocol is the block size. Because what are you doing? You have a cache miss, you are not bringing a word, you are bringing the entire block, right? So suppose let's try to play out the scenario here where the block size is 8 words, and you have a single word that is alternatively written and read by 2 processors. So you have 2 processors that are alternatively writing, reading only to one word, but it belongs to a block of 8 words. What is going to happen? You are bringing in 8 words at once, A to B, A to memory to B, A to memory to B, right? Continuously being putting pressure on the bandwidth between the CPU and your memory, cache memory, right? So that's going to result in increasing the coherency bandwidth demands, because we are exchanging full blocks, not single words. Only single words were being written, but we are not changing that. We are doing it for the entire block of 8 words. The problem becomes even severe as the number of words per block increase. So suppose you are trying to go for a wider and wider memory, then that problem is going to keep on increasing, right? So you can say that if your number of bits in the cache index are pretty high, then that's a way of reducing this problem, because then that would mean that your number of cache lines are a lot, which indicates a sort of a vertical memory, not a wider memory. So another solution here is a directory-based protocol, where there's a directory that maintains the global view of coherent state for each block. So each block, who has it, what is the particular state, right? Like a global view of a block is maintained in a directory. Now, instead of broadcasting that to all the processors are going to send coherence request to that particular directory. I'm trying to access this particular location. What is the status on this? What is the block status on this? The directory then informs the other participants that care about this. That okay, processor A has requested for this, and they have this particular cache. All the other, so it updates that global view, which means that if any other processor is interested in that same block, they are going to know who has access. Go ahead. It requires a slightly higher implementation just because of maintaining that directory than snooping protocol, but it does reduce traffic between the cache and between the caches, and thus you can scale this to higher processor counts. So instead of just exchanging data between processors, what you're doing is all that information, I'm going to keep it in a directory. So whoever is interested, just go look in the directory to get the information about that particular block. Depending on that, you bring that memory information from your memory to the cache, as opposed to you changed it, you give it to others. You changed it to give it to others, right? Keep exchanging data between the caches. All right, that is it for the lecture today. I will stop recording. There's an activity that is due tonight, and I will see you guys on Thursday for operating systems.